Well, thank you all for showing today. The reason schools and conferences have a cocktail the night of at the end of the first day is to test who has the courage and the strength to show up the next morning. And not very many of you do. And as you can see, I already dropped the whatever. So just pick up where we left yesterday. I'm going to show you with ingredients that we discussed yesterday, we can introduce the standard model of particle physics. And it's based, so the way you specify a model in particle physics is you start by giving a symmetry group. In particular, we're interested in the gauge symmetries, the local symmetries. And then you also specify what fermion fields you might have in the theory, which will represent the matter. And then also maybe some scalar fields that can be matter and also give rise to spontaneous symmetry breaking. So in this standard model, you have a gauge group based on actually the product of three groups, SU3, SU2, and U1. U1 is just we didn't introduce it yesterday, but that's a group of phases, pure phases. That's exactly what happens in electrodynamics. So that was the first one we saw. We just didn't call it that. And remember, for each group, there's n squared minus 1 gauge bosons. So for SU3, that means there's 8. Those are 8 gluons that are responsible for the strong interactions. And then SU2 has 3, and U1 has 1. And those 3 plus 1 together account for the particles responsible for weak interactions, the W bosons, W plus and W minus, and the neutral Z boson, which is also part of the weak interactions, and of course the photon. And that's it. Now we have to just specify the fermion fields, or the spinors. And there's a whole bunch of them. To explain the notation, I'm going to give you one example, and I'm going to just list them. There's something called a quark, a left-handed quark doublet. So this stands for a spinor now. Q just to remind you, it's a quark. So it's one of these vectors which are two-dimensional. Actually, it's a two-component object under this SU2. And it's also a three-component object under SU3. That means that it has color. And being a two-dimensional object under SU2 makes it transforming the fundamental representation of SU2, and a three-component object of SU3 makes it also transforming the fundamental representation of SU3. You see, I'm starting to have trouble because of the wine last night. So, and then for U1, since it's just a phase, you have to just specify a charge. You know, when you rotate by a phase, there's a coefficient in front. Do you remember for electrons it was -1, for positons it was +1. And so we call that charge, it's not really charge because it's not electric charge, so we call it hypercharge. And we denote it by the letter Y. And in this case, the hypercharge is 1,6. And so we denote this thing as by this notation: 3 for a triplet under SU3, 2 for a doublet under SU2, and triplet and doublet just means this, what I just described. And then this subscript here means that's the hypercharge. And now with that introduction, I can give you the list of the particles in the standard model. So this is the one we just saw. And then there's right-handed fields, one associated with the up quark, one associated with the down quark. And they're both triplets under color, but they don't transform under SU2. The one here, we call it a singlet, but it just means it doesn't transform. It's just one component. And the hypercharges here are 2/3 and -1/3. And then there's these fields that don't have color, and see if they don't have color, they are what we identify as leptons, because leptons are things that don't carry strong interactions. And there's a left-handed doublet with hypercharge -1/2, and a right-handed singlet under SU2 with hypercharge -1. And charge, it turns out, once you do spontaneous symmetry breaking and whatnot, which I actually didn't write down very explicitly. Oh, well, too bad. So what happens here is SU2 cross U1 spontaneously breaks through this Higgs, broad angular Higgs mechanism that I described yesterday, and leaves behind a U1 subgroup that is unbroken. And that unbroken U1 subgroup is electrodynamics. And so you'd like to know what is the charge of those fields under that U1. But that U1 is a combination of a phase from here and one phase from that. And that combination is actually given by this sum, T3. Remember the generators of SU2. One of them is T3, and then Y is this hypercharge. So electric charge is just this sum. And just to give you an idea what that means, let's take this first example that we looked at. And remember, this is how things transform under SU2. So this is a doublet. So doublets are Pauli matrices. So here's the Pauli matrix times 1/2. And then Y, we say is 1/6. So it's 1/6. And because it's an overall phase, it acts equally on both components. And if I add these two numbers, I get this matrix, 2/3 and -1/3. So this QL has two fields, and it's a doublet. The upper one has charge 2/3, the lower one has charge -1/3. And you notice that there's also these two objects, up and down quarks, with no SU2 singlets under SU2, meaning this contribution here is 0. So their charge is just their hypercharge. And you see these also have charges 2/3 and -1/3. But these are right-handed fields. And if you add together a right-handed field and a left-handed field, you have a complete Dirac fermion, which is the quarks that we're used to, or we want to use for describing the quarks that make up protons and neutrons and so on. So this is the way that the standard model accounts for up and down quarks, with the interesting distinction that the left-handed quarks are the ones that participate in the weak interactions, but not so the right-handed quarks. And that breaks parity. We talked about parity yesterday. And this is one of those examples in which parity cannot even be defined. Because if I make a parity transformation on this subject, I will get a doublet which is right-handed, but there isn't one in the standard model. So weak interactions breaks parity really badly, and this is how it does it. And the same thing happens with the leptons. You see this is a doublet, and this is a singlet. And if you look at, I'll let you do the exercise of checking that this doublet has two fields. One, the upper one has charge 0, the lower one has charge -1. The -1 charge is like the left-handed part of the electron. This is right-handed part of the electron, and both together make a Dirac fermion. And then you're left with a left-handed 0 charge object in here, which is a neutrino. And then in addition, to complete the model, there's a spin 0 object, which has no charge under the color interactions of the strong forces. But there are doublet under SU2 and as hypercharge 1/2. And it's useful to have its complex conjugate, which is also a doublet under SU2, but has charge -1/2, and you'll see why in a second. But this object is very important because when it gets a vacuum expectation value, it breaks SU2 cross U1 down to a U1, which is generated by this combination, as I said. Now I'll show you that momentarily. Here it is. So as I said, SU2 is generated by this type of phase. So there's three generators, Pauli matrices with three functions that are arbitrary, and that gives you three symmetries, and therefore there's three flat directions in the potential. And then that means that instead of one field being eaten by this mechanism, there's three fields that are being eaten. And that says that three of the gauge fields in that list of 8 + 3 + 1 gauge fields that I showed you before, 3 become massive, and that's the W plus minus, and it's 0. And in a slightly more detail, but not much more, when you get an expectation value of this Higgs doublet, this is a number, just like we had before for the single scalar field. This is a number, and you can choose the number to be anywhere you want in this two-component vector, because as you move around that minimum, there's a point in that minimum which looks like this. You can see that just by taking this and making a transformation by this matrix, and that generates all of the possible minima. So the general way to do the expansion is you say, well, the field, as you start from this expectation value, and you add to it some perturbations. And here's the perturbation that is not eaten. And that perturbation that's not eaten, that's the one that's going up and down the potential. That's called the Higgs particle. Okay? And it's massive. And then the other directions are these eaten fields. Okay, so that's in essence what's happening. And of course, the details, you have to work them out. You can get an idea of what the interactions are just from the Lagrangian, but it's kind of nice to understand them just in terms of the Feynman diagram. So again, from kinetic terms, you get just these one-line propagators. I don't have to repeat them to you because it's the same in any theory. But then from the term that couples the covariant derivative gauge field to the quarks, for example, you get several terms. For example, the up quark has colors, so couples to the gluons, and it also has is a doublet, so it couples to the Z boson, and the W makes the upper and lower component of the doublet coupled to each other. So you have interesting diagrams like these, which are very unique, where you take an up-type quark to a down-type quark. So it changes the type of quark when you have an emission of a W. Notice that that's kind of happening with the color index already. You take one color, change into another color when you meet a gluon, except that the colors are kind of democratic, right? To make a proton, you take all colors together and somewhat average over them. Whereas here, making a distinction between up quarks and down quarks is the difference between a proton and a neutron. So that's kind of different physics. In addition, there's terms like these in the Lagrangian that we haven't talked about, but those give rise to couplings of quarks to this Higgs particle. They're also important because they give rise to the masses of the quarks. So when you replace this field by the expectation value, this looks like a constant times a product of two fermions, and those are masses. And finally, there's something, well, the gauge self-interactions we've talked about. And then there's one interesting new thing, which is that, we didn't talk about it yesterday, but these scalars, when they have a quartic term, remember we had a quartic term for this kind of bottle, bottom of the wine bottle potential. Those also produce self-interactions of the Higgs particles. So there's a cubic interaction and a quartic interaction. And you'll see that in some of the things that you might study in the future. We're not going to use it today, so I'm going to just move on. Let me talk about neutrinos briefly. I just mentioned that when you take these interactions, these cubic terms, and you replace the Higgs field by its expectation value, and there's a coefficient in front, which is like a gauge, like a coupling constant that measures the strength of the interaction. But that number times the expectation value, which is also a number, is the coefficient of strength of these bilinear, and that gives rise to it can be interpreted then as a mass, and that's what where the mass arises for quarks. And because this bilinear only has a bottom component, you can check that. Well, maybe have them backwards here, but you can check that this only couples the up quark to the up quark, and then the complex conjugate only couples the down quark to the down quark. Yeah, I actually have it correct. And then when you do the same thing for the leptons, there's only one term you can write down, and that couples the electron, the right-hand electron to the electron, and that gives you the mass of the electron. And then there's a leftover field, which is the neutrino, the left-handed neutrino, which is at the top here. But there's no right-handed neutrino field that I can put in here in this list to make a mass term for the neutrino. There's just nothing like this. So in the standard model, the neutrino is massless automatically. There's nothing you can do to make it not massless, other than to change the model and add more stuff. This used to be a great success of the standard model because neutrinos were thought to be massless, and this comes out automatically. You don't have to do anything special. It's not such a big success now that we know that neutrinos do have mass, and you have to do something about it, and that's a big field of research, exactly what assumptions you make in order to give neutrinos masses. And that's going to be settled experimentally, and we don't have time to talk about it. So let me give you just an example of how the standard model works. Beta decay, which is kind of where the whole story starts. So remember I said W plus minus change flavor. They do this thing where they take a D quark into a U quark and make a W minus. I showed you the opposite one before. A U quark goes into a D and make a W plus. Same thing. Oh, here it is. And I told you also that these kind of diagrams correspond to some specific quantity that you can write down. It's not just diagrams that are pretty pictures that also give you a lot of intuition of what's happening. There's actual numbers associated with it that allow you to compute amplitude. So for example, this diagram is associated with this big expression here. It has some things like these U's here are Dirac spinors that characterize spinors of specific momentum and spin. So here's, for example, a Dirac spinor for this down quark coming in with momentum PD and spin SD, and there's one for the outgoing quark, up quark. And then this W vector boson has a polarization, there it is. And then there's some Dirac matrices and some coefficients and stuff. So it's really, there's really a lot of information. Often we write this by ignoring the spin, what characterizes the particles, like the spinors and the polarization vector, and then it becomes a much simpler expression like this. I haven't talked about this VUD. I'll talk about it momentarily because it's interesting. But then what happens when you do beta decay, you can put these things together. Like here's one of those vertices, here's the other vertex of the W with quarks here and with leptons there. You recognize this is beta decay, I hope. Neutron goes to proton, electron, neutrino. And then when you do this, there's some form momentum carried by the W, which is the difference of momenta of the D quark and the U quark here. So let me call that Q, which happens to be also the sum of the form momenta of these two outgoing particles, PE and P nu. And then you can put together the amplitude for these, roughly, I'm not going to go into details, by multiplying together these vertices. There's a G2 over root 2 twice, one here and one there, so that's the square. This VUD is associated with the down to up transition. And most importantly is this propagator. We talked about propagators yesterday, and that's really what I wanted to bring up. There's a 1 over Q squared minus M squared. And this Q, being the momentum of the electron and the neutrino, is of the order of an MeV. And the mass of the W is of the order of 100 GeV. So that's about a factor of 10 to the 5 difference. And that's really squares. There's a factor of 10 to the 10 difference. So this number, Q squared here, is about 10 to the 10 smaller than this. You can neglect it. And if you neglect it, then this product of terms, which I wrote here, it's just a whole bunch of constants. There's no dynamical information. And so that combination is called the Fermi constant. And this is an interesting concept, actually. Conceptually, what we've done is ignore the presence of the W and thought of this as a transition where everything is happening at a point, like the D quark goes to a U quark and an electron and neutrino, and this whole thing characterized by some constant. And so there's a whole thing that I can't describe, it's called effective field theory, where when particles are very heavy, like the W, you can describe the interactions in the absence of those particles and makes treatments much simpler. And you might have actually been introduced to weak interactions by talking about four fermion interactions and the Fermi theory. And that's exactly how you'd recover the Fermi theory from the standard model, by doing this type of approximation. But I have to move on, and there's a lot of really good stuff coming. So Of course, what I told you was up course, down course, and so on, but there's 3 copies of these spinors. For example, for these quark doublets, there's also, in addition to this result, there's one with charm and strange, another one with top and bottom. And for this, what we call the singlets, in addition to up and down, there's also charm, top, strange, and bottom. And then for the leptons, likewise, in addition to electrons, there's muons and taus and the corresponding neutrinos, and also for the corresponding singlet. So there's 3 of everything. A big question in particle physics is why 3? Why not just 1? Why not 7? Whatever. We don't know, by the way. If I knew, I would be happy to tell you. And one thing that happens in the standard model, which is as a result of the fact that you have 3 generations instead of 1, is that the coupling of the W, and only the W, none of the other fields, to the quarks, and only the quarks, not the leptons, is not just this G2 over root 2, but it's, and it doesn't just go from one doublet to itself. It actually can connect say the upper component of a doublet to the lower component of any one of the other 3 doublets. And there's a coefficient that measures by how much that happens, this Bij, that tells you what is the weight that you give when you go from the lower component of the doublet I to the upper component of the doublet J, where I and J go over DSB or UCT. So I wrote out all of the components explicitly. Because actually we refer to them that way. We have these big discussions or conferences about the measurement of VCB or VUB, for example. Just very, very heated. But because the overall strength of the interaction cannot change, basically the sum of the squares of this matrix has to be 1. In fact, it has to be a unitary matrix. I wrote it here. So it turns out that this unitary matrix, and once you take into account you feel freedom to redefine fields by phases and so on, can be parameterized by 4 numbers. And this is a very good approximation. I don't want you to pay much attention to it, other than to tell you that lambda here is a parameter you can measure. It's called the Cabib angle. It's about 1/10, or actually 2/10. So there's a hierarchy here. There's basically 1s along the diagonal, and then about, a tenth here, 1% there, and even a factor of 0.2 smaller there. And notice that there's a rho minus lambda, rho, and eta, and A are all real. So this is a complex number, and this is a complex number, and it has to be like that from unitarity. So once you decide this is complex, making sure that V dagger V is equal to 1 ensures that this is of that form. In fact, unitarity also fixes this number and that one. And I'm leaving you as an exercise for you to check what this number is. Now, why is this interesting? Because this is complex. There's no way around it. You can't define away this number. And we said, yes, they have complex coefficients. You break CP. If you only had 2 generations in the standard model, you could demonstrate that you can always rotate phases away and you would have a real matrix. So you have to have 3 generations in order to break CP. And CP then is measured by how different from 0 eta is. So you want to establish CP, you measure eta somehow. So here's a whole bunch. This is the rho eta plane, where rho and eta are these 2 numbers. And I'm not going to go into how this is extracted. I could tell you in great detail. Ask me over lunch, and I can spend hours and hours and hours telling you. But each one of these things, sine 2 beta, epsilon k, alpha, VUB, delta MD, delta MS, gamma, they're all independent measurements. And each one of these quantities depends on the parameters of the standard model through some different combination, so that in the rho eta plane, VUB is a circle around the origin, and delta MD, delta MS is a circle about this point, 1, the 1,0 point, and so on. And you see that the only point where all of these measurements agree is on that tiny little dot there. And that tiny little dot is a gazillion sigmas away from 0, which establishes that CP is violated in the standard model. A gazillion is not a very standard unit. And that tells you how well I prepared for this. Okay. So let's move on to something a bit more theoretical, if that was not. Let me talk about grand unification, because I think this plays a role in cosmology and in the thinking about what got us to think about inflation and things like that. And it's really cool, actually. Let's see. I'll show you why I think this is cool. So now let's consider a case where the gauge group is SU5. So SU5, for example, is kind of interesting, has n squared minus 1 is 24, so it's 24 gauge fields. It's pretty big. And what you can do with SU5 is you can spontaneously break the symmetry, we've been talking about that, to SU3 cross SU2 cross U1, that hopefully you recognize, that's what we introduced 10 minutes ago, or 20, as the standard model. So you have a case in which you could start from a single gauge group with a single gauge. Oh, I should have said this. Shoots, I don't think I wrote it down. Well, I don't have to go back to show you, but each one of these gauge groups comes with its own gauge coupling constant. Right? So there's the strength of the interactions of the color interactions is very different from the strength of interactions of, say, electromagnetism, in fact, by a factor of 10. But that's accounted for here because each gauge group can have its own coupling constant. The rotations by gauge parameters are completely independent. But here, there's only one. So when you break the symmetry into SU3 cross SU2 cross U1, all of these three objects are characterized by the same coupling constant. I'll say something about what happens momentarily. But another question is, so how do you actually put these fields together that I went through? And consider a vector of SU5, meaning the fundamental representation, a 5-component object. It turns out in a 5-component object, you can fit in a triplet of color and a doublet of SU2. And the doublet of SU2 we can immediately recognize as these 1,2 minus a half of leptons. And the triplet here on color, you can actually recognize as the charge conjugate of the right-handed field, which I told you yesterday is a left-handed field. So this is basically the complex. This is a complex conjugate. The complex conjugate of 3, 1 minus a third, which is a 3 bar. I missed the bar here, meaning it's an anti-triplet of color. These are complex, so the 3 and the 3 bar are just the complex conjugate of each other. So I forgot that, sorry. And of course the charge goes from minus a third to plus a third. So that's what this is. And it's kind of interesting that it all fits into one 5-plet. So that leaves me, if you count how many fields there are in that first generation, of course, that leaves, and leptons, that leaves me with 10 more fields to account for. So where are they? Notice I'm going to represent these as this triplet and doublet. So 3 components here, 2 components there. It's easier to visualize. Here's the other 10. The other 10 are kind of interesting. I cannot fit them into other 5s because the 5s have to be these by the way that they transform under this group and how this group fits inside that one. But it turns out, if you look at the antisymmetric tensor, an antisymmetric tensor is you take a vector, psi I, and another one, chi j or something, and you multiply them, and then you make an antisymmetric combination. That transforms as an antisymmetric tensor, right? You've seen that in other contexts, but it's the same idea. So here's a 2-index antisymmetric tensor. You can think about it as a matrix. It's 5 by 5. Antisymmetric means zeros along the diagonal. The bottom half of this matrix, I don't have to tell you what it is if you know the upper one, because it's the negative of the transpose. That's what it means to be antisymmetric. And here's how things fit in. You might recognize these guys as the doublet of quarks, the left-handed fields. This is the upper part of the doublet. This is the lower part of the doublet. And it comes in 3 colors each. The right-handed up quarks, which are made a singlet, it's again the charge conjugate that holds here, which is a left-handed field. I have to put all left-handed fields together into a field. So that's why this is what appears. And so they fit here. And then the right-handed electron field, its charge conjugate is a left-handed field, and it fits there. So this can be said as you know, the 10-dimensional representation, which is what this is. By the way, 10-dimensional, an antisymmetric 5 by 5 matrix, has 5 times 4/2 elements, so that's 10. So this 10-dimensional representation has this quark field, the quark doublet, the right-handed up quark charge conjugated, which is that, and then the right-handed electron charge conjugated, which is that. And that accounts for the whole generation. So now you need a 5 and a 10 instead of this whole list that I had before. Well, that. So instead of these 1, 2, 3, 4, 5 fields, I only have 2, and they all kind of fit together. So I always think this is very beautiful. And this is, if you ever go to Madrid and you don't have enough money to pay for the Prado, you can see Goya masterpiece for free at the Ermita San Antonio de la Florida, which is where he's also buried. So anyway, I think it's very beautiful. One more thing which is even more beautiful, but I won't be able to talk about, you can take these 15 fields plus one additional field that you can interpret as an additional neutrino that can be responsible for the mass of the neutrino into a single 16-dimensional representation of another group, which is O10, SO10. I'm not going to talk about it because I can't introduce SO10 and then this type of representation, which is a spinor representation. But you can put all of them together into a single representation, which is even more beautiful. But I don't have a picture more beautiful than this, so I can't talk about it. But here's what I was telling you before. Sorry about this picture. I got it from the internet, and I was lazy to look for another one. But basically, the idea is this theory it has a single gauge coupling. So this is an energy scale. And if you probe the theory at energies very, very high, it really behaves like SU5. If you probe it at low energies, because spontaneous symmetry breaking is associated with a very high scale, in this case it's around 10 to the 17 or something like that, you get the same thing that we saw in the standard model, the W decoupled in the standard model. In this case, the gauge bosons that are not part of SU3 cross SU2 cross U1 just completely decouple. You can forget about them. And you end up with SU3 cross SU2-1, which has 3 different couplings. And the 3 decouplings in a gauge theory actually change strength depending on the this energy of the interaction that you're using to probe them. So, you take electrons, electron, positron, and you collide them either elastically or inelastically into mu plus, mu minus. The strength of that interaction, which you think is just the defined structure constant, alpha equal 1/137, actually it changes with energy. By the time you get to 100 GeV, which is about the mass of the Z bosons, that 1/137 becomes 1/127. It's like a little less than a 10% increase. So the electromagnetic interaction increases. So this is wrong. This is why I say this is lazy. Increases. Well, the strong interaction actually decreases with energy, and eventually, all 3 meet at the scale of grand unification. So this is not a very good picture, but it reminded me to tell you the story that these 3 couplings are different because when you probe them, they're different under different energies, but where you probe in the theory at the grand unification scale, you wouldn't see any difference. They would all look the same. And this is one of the other. The 2 beautiful things about grand unification is the unification of the couplings into a single one. It's just one force. There's no 3 forces, weak, electromagnetic, and strong. It's just one, the grand unified. And the unification of all of the colors with leptons and quarks and leptons and so on. These very heavy gauge bosons that I just mentioned have the property that they connect the upper part of this 5-plate to the lower part of this 5-plate. Those are the gauge bosons of SU5 that are not SU3 cross SU2 cross U1. So here's a diagram which has one of those guys connecting, for example, to the 5-plate on one side and the 10-plate on the other, 10 meaning 10-plate, 10 components. And you notice that this thing, if we write it differently, has 2 up quarks and a down quark going in, and an electron going out. This can mediate proton going to pi 0 plus, it violates baryon number, it violates lepton number, and it can give rise to proton decay, which is a disaster, because protons, as far as we know, are stable. The reason we think this energy scale has to be very large is not just because that's where all of these coupling constants get together and unify, but it turns out to be also the bound that you can put experimentally on the mass of this object, which has to be very, very large. Remember, you have a 1 over mx squared in the amplitude. It has to be humongously large to make sure that the lifetime of the proton is long enough that it doesn't violate experimental bounds. So it's kind of interesting that it all kind of hangs together, that the unification scale is kind of comparable to the mass that we get from experimental bounds on the lifetime of the proton. And people are still looking for a proton to decay, but it doesn't want to. Okay. So let me move on to something which is related to grand unification in a way that will become clear in a second. And this is of interest also in cosmology and in astroparticle physics. And it was mentioned yesterday, so I'm going to go into maybe a little bit more detail than what you saw yesterday. So let me consider a 1 plus 1 theory. So this is a theory with one space dimension, and of course it has time. So that's what I mean by 1 plus 1. So fields depend only on x and time. And let me take phi to be a scalar field that we saw yesterday. And let me take a potential which is something like this that we saw yesterday. It can be an arbitrary function, but with, say, 2 degenerate minima like this. And this lambda phi to the 4 that we saw yesterday plus mu square phi square would do. And the question is, can we find finite energy non-dissipative solutions? A dissipative solution is one in which, if you compute the energy density locally, T0 is 0, for those of you who think in terms of general relativity, but just the energy density. And you start with some configuration at some time t equals 0. And that thing generally is not 0. But if you let an arbitrary configuration evolve in time, typically what happens, it goes to 0 everywhere. Okay. Non-dissipative means that as time goes to infinity, there's some region of space at least where it doesn't go to 0. That's what it means to be non-dissipative. Typically that doesn't happen. Typically you start with some configuration of a field, and it has lots of wiggles and so on, and over time the wiggles just go away, just iron out. Now to answer that, and the answer is that yes, you can find some here. I'm going to explain that. To answer that question, I have to tell you what the energy is. I want to have finite energy. So here's what energy is. You can derive it from the Lagrangian density, but there's a kinetic energy. There's a potential function that we have, and then there's a gradient energy. This gradient energy is associated with, in the Lagrangian, when you have a covariant theory, you have a dt square minus the x square. And then you go from the Lagrangian to the Hamiltonian and define the energy, you get this term. You've seen this also when you've studied strings, for example, in elementary physics. So in order to have energy which is finite, solutions which have finite energy, so I want to look at a fixed time configuration and then evolve it in time, and that's what I'm going to be thinking. But if the potential is non-zero over an infinite region, then clearly this integral is going to diverge. So I have to have the potential be non-zero only at most in some finite region, right? And that's interesting. Notice that I set the minimum of the potential at 0. If the potential I had set it up above that, then there would be an infinite constant added to everything all the time. So I might as well just subtract it away. I've done that. So here's the solutions that have finite energy. There's a simple one where phi as a function of space is just equal to a, just a, where a is this constant. So you have your potential, the field sit there. This is finite energy, and it's kind of what we've been thinking of all along, right? When we talk about spontaneous symmetry breaking. But here's another solution. When x is large in one direction, the field sits here, and when x is large in the other direction, the field sits there. And then, because it has to be a continuous configuration, otherwise, a break would give you infinite energy because of the derivative term. Somewhere, the field has to move from here to there, which I wrote here in this. This is the field as a function of space. And what happens is, there's energy associated with this hump when you integrate over all of space. This gives zero. This gives zero from the potential itself, the potential function. But this piece gives you something which is the integral over this curve. And then in addition, you also get some energy from the derivative term. And so the derivative term wants to make this slope very small. So you want to the derivative will want you to have a thing that looks just like this, very, very flat. Whereas this potential wants you to stay as close to a step function as possible. And the competition of the two gives you a nice smooth function like this. This is called a kink, and you cannot undo it. This is stable. And the reason it's stable is that in order to undo it, you have to break this, but that takes infinite energy. So this thing can move, so you can boost it. The center can be, I put a center here. You can think of this as the energy, think of the energy as a lump of energy which is concentrated in this region. And that lump of energy can move. It has a center. It looks really like a particle. And it's topologically stable, as I said. So you can put little wiggles on this solution and wait enough time, and they're going to dissipate. But the step doesn't. Why do you care about this? Well, imagine now I take this thing, which is in one spatial dimension, and just copy it into 3 dimensions. So there's one direction here, which is the x direction that we had before, and the field does that. And then the other 2 dimensions just go along for the ride. So basically, you have half of space, just like we have here, but half of space now, 3-dimensional space, at value minus a, half at value plus a, and then in between, there's this sheet. Instead of a point here, is now a 2-dimensional sheet over which the value of phi changes from minus a to plus a. So this is a domain wall, and people study this in cosmology, the possible creation of domain walls. I presume somebody will talk about something like this. I tell you later why this could happen cosmologically. But the point is, one of the problems with this thing that I just wrote down is that, of course, there's energy associated with this transition here. We said that in 2 dimensions that was a finite, 1 plus 1, that was a finite quantity. But now this finite quantity multiplied by the area of this, infinite area of this wall is infinite. So it has infinite energy, but what can happen, of course, you can take this thing and kind of wrap it around in a very, very big sphere, for example. It's no longer stable, but it has very long lifetime. And so you can have things like these, which could happen in the universe. You can have, if you have a field which has 2 different vacua, you can imagine having bubbles like these of one vacuum plus A inside the other vacuum minus A. Okay. So can we do the same thing in 2 space dimensions plus 1? Well, you would like to do that, and one way to do that is having a field that has 2 components. So think of a scalar field, which now is a little vector in some sort of internal space. And so here's x and y, actual space in 2 dimensions. And these yellow arrows actually denote the field pointing in this internal space. And you can see that kind of wrap it around a center. And then if I want phi to have the magnitude equal to whatever puts you at the bottom of that Mexican hat potential, then if if I try to move this all the way to the origin, I have a problem because there's going to be some sort of discontinuity. You can see this thing jumping into the opposite direction, and that's true in every direction. So in order to make this behave nicely, there's going to be some sort of center here where the field has to move away from phi equal A and kind of connect sides here. So it has to go to the origin at the center of this configuration. The problem is that even this configuration has infinite energy. And the reason is just that in 2 dimensions, the thing that we set up for the kink, when you integrate over all of the 2-dimensional space, still gives you something which is infinite. So I try so here's how that happens. Here's again the energy expression. Remember this arrow for phi just in some internal space. Let me use polar coordinates, rho and theta, for the energy. So you can see that, if you integrate over theta, you get some 2 pi. But the integral over rho, which is a rho de rho, and if you think of the gradient here, I'm putting phi to be this constant A times a unit vector, which is pointing out. So that it connects the space with internal direction in the internal space of phi. So this is physical space to that. That's what we have in the picture. When we take a derivative with respect to theta of these, there's a 1 over rho squared d theta, you get a squared over rho squared, and the integral from rho d rho to infinity diverges. So how do you fix this? And how do you get finite solutions? If you gauge this internal symmetry, these arrows pointing around, so instead of a derivative like I had here, you make this a covariant derivative with a field A, which is like a photon. The generator here T that I have is like a emission matrix that just mixes the 2 components of this 2-component internal space vector. So now what happens is, because you have these 2 terms, this 1 over rho d theta phi can be cancelled by choosing this gauge field carefully. Okay. Now I'm not going to solve the equation for you. You can solve it actually analytically, but I'm not going to solve it. You can get an idea of what's happening just from this. This is the same picture as before, but I put these purple arrows that represent the gauge field A, and it points in the theta direction because the rate of change of the yellow lines, of the yellow vectors, came from d theta, right? The derivative with respect to theta, so it's a theta that has to cancel it, and so I choose a to be in the direction of the rate of change of this phi field, and then you can just arrange for the magnitude to cancel the other one, and you get a finite energy solution. So great, so now we have a finite energy solution. We can repeat this story that we did with kinks, but this one additional ingredient. If you look at this vector potential, this is like it's a U1, it's like in electrodynamics, except it's some other fake field. You see a circulation here, right? Now, from electrodynamics, you know this. If you have circulation, there's a magnetic flux. The flux is B dot n, where this is over a surface which is a circle out here. There it is. B is the curl of A. Then you use Stokes' theorem. You write this as the circulation, ADL. And the ADL is actually pretty easy to compute here because A is completely determined by this field phi. And it turns out that it just measures by how many times you rotate the field as you go around. So these two, I'm not going to do the computation for the U, but you get this 2 pi over e times n, where n is the number of rotations of phi. So not only you get this solution, there's other solutions where instead of rotating the field once, you can rotate it twice as you go around, or 3 times as you go around, and so on. It's an infinite set of solutions. The picture has n equal 1. So now, I have minus 20 seconds, but let me go on. I'm going to do the same thing as before. I want to go to 3 dimensions so we can do what happens in cosmology with this. So here's this plane that we had before with these arrows pointing away from the center, and then these purple arrows making this circulation. This field, I forgot to say this turns out to be a pure gauge field, meaning there's no actual electric and magnetic field out here. I did say it, but I did write it, I didn't say it. But close to the origin where this thing happens, when the changes happen, it actually becomes a real field. And it has to because there's flux. You know that, right? So now you multiply this solution into the last dimension, the z direction, for example, and what you get now is a tube, or a rope, or a string, or whatever you want to call it. So it looks like vacuum everywhere, so the vacuum is changing in direction. Except in this rope or so on, there's a magnetic field with a flux which is quantized, 2 pi n over E. So these are called cosmic strings, which I cleverly wrote in yellow so you cannot see it. And again, they have infinite energy because it's finite energy configuration in 2 dimensions. You multiply by infinite length in one direction, it's infinite. But you can do the same trick as before. You can loop them around, and you can have several of them, and you can intersect them and do things, and you can interlace them. And there's been studies of theories of dark matter were based on this. Okay, so I know I'm out of time, but let me just mention this very quickly. We did 1 plus 1, you do 2 plus 1, what comes next? You do 3 plus 1. So in 3 plus 1, there's solutions. They're completely analogous to the 2 plus 1 hedgehog that we just saw. Which is what I say here. They have finite energy in 3 dimensions, so you don't have to do this thing where you expand in an extra dimension. And they look like little balls of energy. And they're also topological. Notice that the previous solutions were all topological in nature. They cannot be broken and make unstable that way because it costs you infinite energy. And you always get one when you have a gauge group, a simple gauge group break into a subgroup that contains a U1, like in the grand unified theory, because grand unification always has to have a U1 at the end, which is electromagnetism. And grand unification means it starts with a simple group. So every grand unified theory predicts the existence of monopoles. It's called a monopole because this thing that we have, this 2 pi n over E quantized flux also happens here. So you've got the flux around one of these balls, and there's magnetic flux that comes out and is quantized. And they're different from Dirac monopoles, which I don't have time to explain because I ran out of time. I'll end with this. I'm not going to talk about inflation. I think there's going to be enough inflation in these talks that I don't have to talk about it. But how do you produce this stuff cosmologically? I'm going to say it in a couple of words. Here's an early hot universe. Here's that potential that we saw for the king. If the energy, kB times the temperature, is well above this hump in the potential, then the field can just be jumping around every which way. And there's really no difference between one vacuum and the other because the field expectation value is given by these large fluctuations. So the expectation value is really 0 because it's just jumping around. So, that's a picture. It's the hot universe is red. The cool universe is blue, of course. When you cool off, the temperature comes down, and then you either choose to be in one side or the other. But you can take regions that are disconnected causally from each other, causally, not casually, causally from each other. And some will choose to be in some vacuum, some in others. You don't know that a priori, and they can't talk to each other, so they can't be in cahoots to always choose one. So as the universe cools down, you're going to end up with a situation like this. And that's how these things can be produced cosmologically. They can be a big problem for theories because they can carry a lot of energy, as we said, as we saw. And that can put bounds on theories. So this is the same thing. So I'll stop there. Thanks for your patience. I went over 5 minutes, and I'll take a few questions. Thanks. Yeah.
Hi, thanks for the nice talk. I wanted to ask if you can comment a bit of on the state of art of grand unification theories, because every time I talk with somebody doing similar things, I get the feeling that there is this insistence of abusing symmetry breaking mechanisms to complicate stuff with very weird gauge groups or matter content. And I mean, sky is the limit as long as you find a PhD student willing to do the job. That's
Yeah.
my feeling. I don't know if it's true or not.
Well, it's true that the sky is the limit if you find a graduate student willing to do the job, regardless of grand unification. So I'll tell you my view on this. I can't speak for the whole community. First of all, it's true that the interest in grand unification per se has decreased over time. I think there's several reasons for this. First of all, there's many other things that are interesting, so why not? But the two, I think, big drivers are one, that the proton does not decay. So there was always that that idea that if proton decays, then we know it's there. And the second problem that has kind of driven people away is that, well, if proton doesn't decay, we don't seem to have any handle on this to reach it experimentally and to establish anything. So, what's the point? However, although people have done all sorts of interesting, convoluted unification schemes with very complex groups and whatnot, it is still true that some of the simplest models are viable. The problems that you might have come across, like the couplings don't precisely unify in the minimal SU5 case, are very easy to solve by adding a few additional particles at low energies. When I teach this thing, I actually was teaching some people that are here today, last week in Madrid. And one exercise I gave, you can add additional Higgs doublets. And it turns out when you have 6 Higgs doublets in the standard model, the couplings unify much better than even the minimal supersymmetric standard model that people were very excited about and has fallen also out of grace. Now 6 sounds like a totally outrageous thing, but there's 3 up-type quarks, 3 down-type quarks. 6 sounds like a good number. I know. So that's one example. There's other examples. And there's quite a bit of excitement that may actually dissipate soon over anomalies in B physics, in things you might have heard about, RD star, RK star. Some anomalies, meaning predictions are not met by experiment, or they're the other way around, in the case of some mesons. And the best explanations typically involve new particles that are fairly light, like 1,000 GeV, 10,000 GeV. Those would actually contribute to the running on coupling constants and may actually make the, once you say there's something else happening, so let me rephrase this. There's no reason why we couldn't have more new physics at some, low scale that would change the picture of what unification is. So I think the unification as a concept is very beautiful, and many of us believe in our hearts that it has to be there because it makes things so nice and so compact. So we haven't given up on it, but I don't think we have a good idea of how to push forward. I've heard people proposing that gravitational wave echoes can be sensitive to new physics at very, very high energies. So if that happens, maybe before you guys die, but after I do, some of these things will be settled. I don't know. Mm-hmm.
Thanks. Can you go to your slide about the GUT? Sorry. My question is actually, is there evidence or are there experiments hinting at new forces emerging at low energies, not forces uniting at high energies?
So new forces emerging at low energies, if by low energies you mean much lower than the unification scale, but still energies of the order of the weak scale, then my best answer to that is we have at the moment these several types of anomalies. And depending on your view, some are to be taken more seriously than others, but you've heard about G-2, you heard about the W mass anomaly, there's RD and RD star. Likely some of these things are gonna go away. They can be experimental fluctuations. But there's a lot of rules. The investigation of these anomalies had made it clear that there's room, given what we know, for additional forces and additional force mediators at that scale. If you're asking about forces at much lower energy, so masses of the order of an electron volt or MeV and so on, there is room for that. Experimentally, there's bounds, but the bounds are very, very tough. And so they have to be incredibly weak forces. You can think of the action as a mediator of forces, and it's not ruled out, but it's incredibly weakly coupled.
Thanks for the talk. Would there be any reason inside of the standard model for leptons and quarks to have integer charges of one another? So
thank you for pointing that out. So the charges, of course, if I multiply the charges, all of the charges by 3, then all the charges are integers, which is kind of weird, right? And why would that be the case? In the standard model, the only reason the charges are connected is actually a little subtle. It has to do with something called gauge anomalies, which I can't touch on. But that it's mathematical consistency of the theory that requires it. Except that in the standard model, to be completely honest, the full calculation for that requires also that you make an assumption about gravitational gauge anomalies. And so we don't really know how gravity works. It's a little bit of a crutch. But if you take that, then it turns out that the charges, the relative charges are fixed in the standard model, and they're what they are. But another approach to that is grand unification. Grand unification, all the charges are fixed relative to each other because they're all part of this one single SU5 group. And so there you have no choice, and they come out to be automatically the ones in the standard model. So that's another, actually, thanks for pointing this out, that's another thing which is very attractive about grand unification. Sorry I didn't have time to tell you about my beautiful things on my inflation, but yeah.
Thank you very much.
Hello. Okay, so I guess I can start. So thank you for inviting me here. I'm very happy to be here and see such a young crowd of people enthusiastic about science and the universe. So my name is Matteo Viel, and I will talk about how to use the universe as a laboratory, right? To test also the things that we heard just in the lectures before. So what you see here in the background is a computer simulation of our universe made for the Euclid collaboration. Is an embodied simulation, very large, in the sense that we have many, many particles which discretize the properties of this fluid, which is thought to be the dark matter. So we will be talking quite a bit about dark matter. So the plan of these 4 lectures is the following. So the idea is to provide you with a set of fundamental tests of physics in the post-ionization universe, providing few snapshots of the cosmic history in terms of structure formation, and to see whether we can use this information to ask some big questions, right? And so the idea that I had is to move gradually from the high redshift universe down to the low redshift. And so we'll be talking today about the intensity mapping, which has emerged as a new technique to probe cosmic structures. It's a field really in huge development in these years. Then I will be talking about the intergalactic medium, which is my main area of expertise. And then the 3rd lecture will be devoted to galaxy clustering, to see how galaxies are traces of the large-scale structure and can be both a probe of the dynamical growth of structures and the geometry of the universe, right? And then the 4th lecture, I will be talking about weak lensing and galaxy clusters. So it's a lot of things, and hopefully we will get through this, and hopefully I will give you an overview. And of course you can contact me at any time to ask me for further papers or ideas, or that we can discuss together. So I will be here the whole week. So natural connections, my lectures are here, even though, of course, there could be many more. I apologize if I was not very inclusive, but of course, Fabio is going to talk about the CMB, as already talked about this. Fear will talk about galaxies, small-scale properties of galaxies, like dynamical structure of galaxies as a probe of fundamental physics. Then there is Luca also talking about modified gravity and dark energy. And then next week, Olga and Tracy Slater will be talking about dark matter and neutrinos. So it's really, a huge set of questions and topics that we're going to be addressing together. So the CMB, right, for us is the initial condition. In the sense also the simulation that you saw before has been run having as initial condition this nice picture here. And this observation of Planck is fitted by a theory which is based on 6 parameters. And this is remarkable because you see the structure that you see here is rich. No? It's complex in a way. You have several peaks and troughs with physics, and is remarkably well fitted by a simple model with 6 parameters, which invokes at very high significance the presence of colder matter, right? This number here at many, many sigma, probably 80 sigma is the non-baryonic, and 140 sigma, which is this number here, is the baryonic matter. So the evidence for a colder matter component till, in the pre-Planck era was just rotation curves of galaxies, consideration by the dynamics of galaxy clusters. But now we do have this very neat, precise, accurate measurement of the cosmic microwave background. And here dark matter is very much needed, right? This is initial condition. And the final condition could look something like this. This is the SDSS distribution of galaxies. So we do have experts, of course, in the audience like Carlos. And so you can really analyze the physics. No? First of all, you can analyze the clustering pattern of this galaxy. You can use summary statistics like the correlation function, the power spectra, the bispectra, and learn about this. And of course, this is a bit more difficult problem, right, compared to the one before, because while before, you have simple, in a way, linear physics describing your observable, your multi-peak structure. Here, the situation is a bit more complex, in the sense that it's very silly to consider galaxies just as points that are tracing the underlying dark matter distribution. There is much more, in the sense that, the overdensity of the tracer is generically a function, of course, the position. Redshift could be a function of the environment, could be a function of physics, like the physics of matter that shines, like stars, interstellar medium physics I'm talking about, luminosity. And this is a complex function that, of course, if you want to dig out fundamental physical numbers like neutrino masses out of the pattern of clustering of galaxies, then you need to take into account, right? And so in a way, we are lucky, right? In a way, we are lucky because we do have initial conditions, and we want to evolve this initial condition down to this last picture that I showed you, throughout 13 giga-years of time of cosmic histories in which gravitational processes, but also astrophysical processes are, coupled to each other to some extent, right? And so it's really tricky to disentangle the two. So in the process of addressing fundamental physical questions in present cosmology, you will learn a lot about astrophysics, right? Which is a byproduct. Some of you might be more interested in astrophysics, some others might be more interested in physics, fundamental physics. So about 40 years ago, something happened, the summer of 1982. Let me remind you what happened. Italy won the World Cup. So since Italy is not playing this World Cup, I'm just talking about the past, I don't want to talk about the present World Cup. Summer 82, we won in Spain, actually. In Madrid, this is Paolo Rossi, who died, I think, last year, and we were very happy. I was a little kid, 7 years old. But in the summer of 1992, there was this other seminal paper by Jim Peebles, which made the following consideration. At that time, those initial conditions that I showed before of the CMB were not measured, right? They were measured a few years after, so he didn't know about this. They were just upper limits. But the large-scale structure was measured, not as neatly as we saw before, but there were a few measurements of some large-scale structure survey. And in a very simple calculation, this paper is just 4 pages, if I remember correctly, he compared the correlation function of these galaxies, better to say, well, some number connected to the correlation function, and he set basically an upper limit to the level of anisotropy of the CMB. And he said, we need dark matter, because if we didn't add dark matter, then we would probably have already observed some anisotropies which we didn't, at that time, were not observed. So this was, I believe, the first paper which made the connection between these two pictures and provided a fundamental physical number. He said we will need some WIMP, let's say weakly interactive particle like this one here of this mass to have things in place. And a few years after, the CMB anisotropies were detected, and then the era of precision cosmology with CMB started basically. And so now the 4 pictures that I want to show you, where even if here I draw just a few lines, are basically in the post-ionization universe after the last scattering surface, even after the so-called dark ages, where the universe was neutral. At some point, the first galaxy starts to have stars. The stars are typically bright. In the UV, they start to ionize. The universe becomes gradually more ionized and thereby less neutral and more transparent to radiation. So this epoch here is a significant epoch of the cosmos. So here we will be looking at intensity mapping, intergalactic medium. And when we will be moving to the low redshift universe, we will use the weak lensing, galaxy clustering, and even more recently towards us, the galaxy cluster, which are the biggest virialized objects of our universe. So it's really, a snapshot, a tomographic, kind of approach to the large-scale structure. So why do we want to be tomographic and multi-probe? I kind of summarize my point of view in this slide. Well, first of all, new fundamental physics is usually well hidden. If you read the Planck papers, the legacy, one of the most important legacy of the Planck papers is if there is new physics, is well hidden. Okay, and then maybe by having a long lever arm in terms of time and multi-probe, we can be more sensitive to the kind of fundamental physics, which is, again, well hidden. Neutrino mass is typically a tiny effect in the large-scale structure. If you had to talk about particle physics, about neutrino mass from cosmology, they ask big proof. They want your number to be robust because they want to design an experiment able to detect or, let's say, not detect this mass or contradict your bounds. Second point, wide redshift range. Why do we need a wide redshift range? Well, can't we just pick one redshift and maybe concentrate our efforts there? No, we need wide redshift because having a wide redshift range allows to break degeneracy. Suppose you have fundamental physics and astrophysical aspects. They are to some extent coupled to each other. But by exploiting the wide redshift range, they typically decouple. It's very contrived to have a universe which at any time, at any stage, will have a fundamental physical aspect which is absolutely mimicking an astrophysical one. So they typically decouple. This happens most of the time by looking at the wider redshift beams. And then, of course, in designing these experiments, you have a mixed set of researchers, scientists, instrumentation, and so you have different expertise, and then thereby you're less prone to systematics effect as well, both in the instrumentation and both in your way of doing science. And then, of course, think about in these terms, if dark matter is not a WIMP, which maybe is less appealing now, and is not an axion, QCD axion, then there is a whole zoo of particles that can be there. And so having many observables will allow to address a richer landscape, and maybe the discovery potential in this landscape is going to be huge, right? It's going to be larger, at least, than focusing on one experiment only. And so, well, having this in mind, I believe that the attitude of you young guys and active, exciting, and excited about all these things, and is that you really need to have an open mind to the things that you can test, you cannot test, and build up an expertise in many different subfields. So in terms of intensity mapping, which is today's lecture, so there is nice review by Eli Kovetz. So I will, of course, provide you with these references later. Here I just listed a few of them. And the point I want to make is relatively new research field. So the plan is to review the basics of H1 intensity mapping, theoretical modeling, big question to be addressed, and we'll conclude with the latest development, with the latest experiments, right, with the latest actual measurements. So neutral hydrogen or atomic hydrogen in the universe. We know that after recombination, the universe starts to gradually become ionized. Nevertheless, there is a tiny amount of neutral hydrogen surviving. At redshift 3, we believe there is one neutral hydrogen atom in 10 to the 5. So it's a tiny amount, but nevertheless, it's present out there. So there might be physical processes which are able to spot this, right? One of them we'll see tomorrow is the Lyman alpha absorption, scattering. And the other one is the 21 centimeter line of neutral hydrogen, which is spin flip transition, which is basically caused by the emission. It's an emission process which is provided by, which happens at 21 centimeter, which is caused by the fact that the electron is excited in this when the spin is aligned and gets to the say a more stable state by emitting a photon and doing the spin flip. Okay, this thing is up and is observed in the local universe in galaxies, but rather than looking at the local universe, we want to look at it, in the diffuse environments, because 21 centimeter hydrogen is diffused. It's not only in the galaxies. So it's not just 21 centimeter H1, but there are also other molecules and lines that are providing intensity, right, in the luminosity. And these are the most popular ones. This is CO, which is the most abundant molecule after H2. Then we have this excited state of C2 is another, these are in the millimeter, this is in the infrared. Then you have H alpha and Lyman alpha, these are more in the UV or optical. And these are really, the processes that you are after when you want to detect galaxies in the IAC universe. Typically, you track these lines with instruments, spectrographs, or photometry, and you see this little galaxy luminosity, and you study large-scale structure in this way, right? Euclid is going to focus on H-alpha galaxies in the IAC universe. All these lines, apart from the 21 centimeter, these four are typically related to the ISM. They're typically related to stars in the interstellar medium inside galaxies, to star formation. Nevertheless, you can use them to do cosmology. So the idea here is the following, right? That why is this H1 so important? Why is this kind of new? The thing is the following. Suppose you want to, we are fundamental physicists in a way, we want to address the dark matter distribution, and we have simulations like those the one that I showed before. You have this volume which is relatively large, gigaparsecs. Then suppose you paint on top of these galaxies. The galaxies that you will observe with a telescope are typically seated on top of the high density peaks of the distribution. So typically these are bright objects that they shine and you observe them. So your telescope will be magnitude limited, flux limited, right? So you will observe only the brightest top, then you can go fainter with the more powerful telescope, but nevertheless you will always sample the brightest spots. But this with intensity mapping, it's totally different, the rationale. It's basically you integrate all the light that comes from this from this emission process. You will integrate it with poor angular resolution, but with exquisite radial resolution. So you will be really blind, kind of, not very, a bit fuzzy in this direction, but very precise in the radial direction. We'll see the consequences of this. And so you will see things like this one. But nevertheless, you integrate out, better to say, you integrate in all the small scales. So in a way, these clouds that you see here will be also produced by little galaxies provided they carry within themselves some H1 or some CO, right? So you do have an access to the smaller scales in an integrated way. This is going to be very important. And this large-scale view can be complemented also with the Lyman alpha forest that we'll be talking tomorrow, which is small-scale structure. So these kind of experiments are relatively cheap. They are meant to survey the sky in a reasonable time, relatively fast. They have access to relatively wide field of view. So they want to access large volumes in a cheap way, building interferometers, building single dishes. So they are kind of much cheaper than this kind of observations, even though, you know, they are, the point they want to make is that we will never substitute galaxies. We will be complementary to galaxies. So just to give you an idea of what you would look like, this is a simulation, it's not an observation. This is some galaxy distributions, and the galaxies which have inside them some CO molecule. They are represented as dots. Then you integrate them and you see really bright spots. And this is really where the CO signal, intensity mapping signal, will come out. So how do you model this? In a very simple way. You model typically, there are several ways of modeling, you write down a power spectrum, which is the clustering pattern of this line, of this intensity line, in the following way. This is the matter power spectrum, which can be linear or non-linear, right? Depends on where you want to look at things at. Then there is this bias, that just takes into account the bias of these tracers. And then there is this intensity term in front of here, which can be linked to the temperature of the 21 centimeter brightness, if you know what I'm talking about. There is typically a shot noise term, which is important at small scale. So if you plot this power spectrum in dimensional units, you have here the clustering pattern information, and at some point the shot noise kicks in, and then it kind of, you know, have this slope here. So this is the luminosity of this DL of these sources, and the intensity is you weigh the luminosity with this function once, and the shot noise term is basically the second moment of the luminosity. So in a way, if you have access to both these scales, the clustering scale and the shot noise scale, the constraining power on these two functions becomes larger, right? And typically what we cosmologists are after is to provide a link between the luminosity, which is connected to the line, to the mass of the underlying halo. And if you have more information, the fact that here this part is weighted by luminosity, this square provides a further constraint to your model. So at the end, we want to model the relation between luminosity and mass of the halo. If it is 21 centimeter, if it is CO, C2, whatever it is, whatever it takes, we can try to do it. So how do people How do people behave in this theoretical modeling? There are several avenues. The first one is to embed empirical galactic relation into halo models, a bit like this one, right? You tell the theoretician, look, I studied the galaxy nearby in which I found some H1, some CO, and I know that there is such an amount of CO that scales with the star formation rate of the galaxy that you observe. And then you provide a link between star formation rate, mass of CO, mass of the halo. Star formation rate, mass of H1, mass of the halo. This is the chain of empirical relationship which will attach fundamental physical quantities to the intensity, right? This is the first step. The second step, which is very popular among the astrophysicists, is to have these semi-analytical galaxy formation models, which basically they do model, right, subgrid physics like the star formation rate of the galaxies, the ISM, cold phase, hot phase. You can be as much complex as you wish. Down to small scale, they embed it into a mass function, and then you can get out of it your observable, right? That's a perfectly sound approach. And then the third approach, which is the most computationally consuming, is to have hydrodynamical simulations. But if you remember what I saw in the beginning, I told you, look, you have this large volume, gigaparsec, right? But also we want to model star formation. So it's really a leap of scale, which is tremendous, from the gigaparsec scale down to the parsec scale. So this approach of using hydrodynamical simulation to go from one to each other is very, very complex, and in practice cannot be done, right, self-consistently. So in terms of halo models, if you want to use instead of P matter the nonlinear matter power spectrum, right? You can plug in some nonlinear prescription that you find in the literature from body simulation, or you can use also these halo models. The halo models for the H1, there are several papers that discuss this, but basically they assume that basically either your H1 is in a halo, and in that case you can basically kind of concentrated in the halo, compute the correlation between these two halo. This is called two halo term, and this is fine at large scales. But when you move to the smaller scales, you must be sensitive to the actual H1 distribution inside the halo, and this is the one halo term. And the total power spectrum is the sum of the two. Okay, not surprising. This one is likely to dominate the large scales. This one is likely to dominate the small scales. And here you can see several quantities that are of interest. This is the mass function, which retains the cosmological information. It could be pressure shatter, whatever you wish. This is the bias of the halo. You can plug in a simple linear bias model. And this is the relation that I was telling you before, that in our case plays the role of the luminosity, which is the relation between the mass of H1 in halo with the mass of the halo, right? Is the translator of cosmology into astrophysical into cosmological information. Is very important. And this is the H1 profile. Could be Navarro-Franken-White, could be something better like this one here, which emerges from simulation. But basically, this is a very simple way to get your H1 power spectrum out of a theoretical model. And people did this and compared to hydrodynamical simulation. This is a work by Francisco Villascusa Navarro back in 2018. And so he has this TNG simulation that you might have heard of. They are developed in the US at CCA. And so you see here, you zoom in, you follow the H1 distribution down to the smallest scale. You see that you have structure. Here you are below the megaparsec scale. Here you are at the order of 10 megaparsec scale. And so you might wonder whether, these small scale structures can propagate out to the larger scales. In practice, right, I told you that you have very poor angular resolution, but maybe this is sensitive to the radial resolution, so they might be coupled to each other. So this is the model that you have. In this case, we brought in also the Redshift space distortion through this term here. This is the shot noise as before. And the building blocks of these models are the mass function, this MH1. And now you can use these simulations to learn the relationship between H1 and the mass of the halo. And so you see here there is a cutoff below which you don't have H1 because these halos are photoionized by the UV background, which is uniform. They cannot carry H1 below a given mass because they are subjected to a uniform UV background that will photoionize them. And then typically the H1 will increase with mass. And it has this form here that you can plug in and see the consequences, whether these parameters, alpha, for example, is degenerate with neutrino mass. This is the kind of question that you're asking yourself. And what else can we say about this theoretical modeling? Of course, this relationship here will have scatter, right? And the scatter might be physical, so it's not maybe enough to implement just the mean of it or the median. You want to simulate the scatter itself. But the building blocks are simply outlined here. So if you don't want to rely on this, CPU time, heavy CPU time consumption simulation, you can just work out your model with few simple Python code within minutes on your laptop, and have a good, a good comparison with the simulation. So you see here this omega H1. It's the amount of H1 in the universe, and it's not a free parameter, likely. So likely this H1 modeling, theoretical modeling, has some boundaries, has some constrictions, right? So for example, what you see here is the actual measurements of the H1 distribution in the universe from absorption lines. And here again are measurements from absorption lines. So the amount of H1 is constrained in the universe independently from this observation, from absorption line studies. So you can use this, you can plug this in as a prior, as a reasonable, robust prior, and this is good, right? Because you have one parameter less probably in your modeling. And this is through the H1. And then you can also, it's much more, let's say, theoretically appealing to cast things rather than the power spectrum in terms of multiple expansion. And so, for example, you can work out, this is the 21 centimeter power spectrum in Redshift space, the thing that I showed before. This is where the intensity goes. And you do the multiple expansion, you look at the monopole and the quadrupole, and you have you have curves like this one. This is again a pure simulation, right? No observation here, and you see that the redshift evolution is really huge. Why is that? Two reasons. First reason, the H1 is evolving, and so we take care of this through the modeling. But second of all, as I told you before, this is a poorly angularly resolved observation, and so the angular size will be different. The angular diameter distance will be different redshifts. So this is cut off at small scales is the product of the beam of your telescope. Whether it is single dish or interferometer, you can calculate it out. And this is, for example, for SKA. But basically, you take out this, and so this dumps the signal. And to some extent, is good because it dumps somehow the nonlinear astrophysics regime, which is a bit more difficult to model, at least in the angular direction, right? The second thing, maybe this is a bit complicated, just focus on this one. The bias of H1 with compared to matter. We would like things to be scale independent, at least at large scale. This is, the ratio of pH1 over p matter. And they tend to be flat at large scales, small wave numbers, but then there is this kind of strong scale dependence here that you want to model. So you must be careful on whether or not your model contains such a scale dependence. Why? Because fundamental physical aspects like the neutrino free streaming show scale dependence. Modified gravity to some extent as well. F of R, right, shows some scale dependence in the linear theory. Maybe nonlinear we don't know, or we do know because we have some simulation. So you want maybe to see whether this is degenerate or can hide some fundamental physical aspects. So these H1 observations are difficult, and some people think that will be made in cross-correlation only. Indeed, the few observations that we'll show towards the end are done in cross-correlation. And so people, they say, okay, we have this n-body simulation, we paint on top the H1 signal, but we do also have galaxies, right? And so we can study a bit better this famous H1 over mass of the halo relationship by really singling out, by really looking at which galaxies contribute most. And so, for example, what you learn here is that for small mass halo, the roles of the central galaxies is much larger. Here are the central galaxies compared to the satellites. But for very massive halos, the satellites are more, contributing to the H1. And so why do you do that? Because suppose you have a survey in which you have this noisy pattern of H1 intensity mapping measurements. It's very noisy. Then you do cross-correlation. You can do two things. You can cross-correlate with the central galaxy, maybe. You can cross-correlate with satellites, and you will see two different things. It will be like filtering out the signal with two different windows. And so the cross-correlation is an effective way of filtering out your complex signal and dissecting into sub-pieces that you can study a bit better. They are a bit more constraining. Okay, so neutrinos. Let's go to neutrinos first. This paper, 7 years ago, we tried to provide some forecasts in terms of neutrinos. So what you see here, just concentrate on this plot here. This is a 21 centimeter signal in a universe in which the neutrinos are present but massless, and two other universes in which the total neutrino mass is 0.3 eV, 0.6 electron volt. And so you see here that you will have a suppression of power of the order of 10, 20, 30% at the largest scales. These are reasonably large numbers, I would say. Of course, here I a bit cheated because I fixed all the rest of I just changed the neutrino mass. Ideally, you want to do this with Bayesian statistics and marginalize over all, the possible parameters affecting the signal. And the point that I want to make here is that this is both a plateau effect, but also which retains a bit of scale dependence. And if you cast this in terms of comparison also with other probes, per se, you will have an error, one sigma error of about 30 millielectron volt. But once you combine this with CMB and with Euclid light spectroscopic survey, this can be tightened a bit, quite significantly. So at the level of maybe 18 millielectron volt. And this could allow to disentangle two hierarchies, right? And so this is something that to keep in mind. In quoting these numbers, we try to be conservative. We tried also, to implement different halo modelings, different nonlinearities, different way of relating the H1 mass to the halo of the mass. So we try to be conservative. This is, I would say, a robust number, 30 millielectron, that can be increased further in probe combination. This is so the first, let's say, fundamental physical question, dynamical growth. But the second that I want to address is baryonic acoustic oscillation. So you know from Fabio, this is in a way the same mechanism at the CMB scale, but some gigayears after in the large scale structure, you will have a leftovers, a leftover of this baryonic acoustic oscillation. And so how do they appear in terms of correlation function? They produce a bump like this one here. You see here, this is the bump, the black line. Then you have two effects. The nonlinearities cancel a bit the bumpy structure, makes the bump a bit less prominent, right? But then the real killing effect of this 21 centimeter correlation is really the angular resolution. Once you smooth this with the angular resolution, you see the bump is not visible anymore. And for 25 megaparsec, you don't see any bump, right? And so when we got this, we thought, okay, we cannot really do baryonic acoustic oscillation with 21 centimeter intensity mapping, right? Because there is no bump there. But this is the isotropic 3D correlation function, when you average this with the radial direction. If you can disentangle the two along the parallel direction and in transverse direction, things looks a bit more promising. And this in terms of power spectrum, there is a consistency relationship between the 1D power spectrum and the 3D one. And you see it works like this, that the 1D is basically related to the 3D in the following way. You suppress this by a given factor, but basically you see in the 1D along the parallel direction, you really still see the wiggliness, okay? So this is outlined here, this is purely theory. You smooth it out, you see you suppress it. The more the angular scale you are smoothing out, the smaller the signal will be, but the bump are still there. So if you have a model which doesn't present any wiggle, and you divide them out, you will still see this wiggliness in the 1D in the radial coordinate. I remind you, these are, this line of 21 centimeter is 1.4 gigahertz. Typically, you sample your signal in many channels, and so the frequency resolution is really good. It's at the level of the kiloparsec, okay, or so. And so you can really sample the line finely. Okay, but we wanted to convince people that you could do things, so we tried to be kind of closer to the experiments in a way, and we mocked not only, the signal, which is this one. We provided a cosmological mask because, of course, you cannot observe the whole sky if the experiment is based on ground. We put the foregrounds. Okay, the foregrounds are a big issue that I will discuss later, and so we remove the foregrounds with PCA component, and we ask ourselves whether this wiggliness can still be seen in the processed data, and the answer is yes. Okay, so here is the different redshifts. This is the cosmology position of the peak. You see it's seen with a precision of 1%. Then you add the noise, it's 2.6%. Then you add the foreground, it's 3%. So of course, the noise, the mask will spoil your signal, will make will make your determination of the position a bit, let's say, less accurate, but still that will not bias it significantly. And so I believe that this thing will be done. CHIME experiment is after the measuring BAO from redshift 0 up to redshift 3. And so this potentially has consequences for dark energy, early dark energy models, modified gravity, because you will be probing the geometrical state of the universe in a range which is still, let's say, not very much investigated. So I told you that in the halo model you need the halo. So you need the one halo term, and the one halo term will use as input the H1 distribution inside a single halo. And so what you see in this compilation of gray line overlapping with each other is really the different set of halos that will display different profiles. And typically the scatter that you see here is something physical. So if a halo has something below or above, there is a physical region. It's not statistical scatter. So in a way, you can have more refined models by investigating a bit the scatter. But the simplest way, the zero order thing, is that you implement these curves like this as a function of mass within the halo model. You plug them in and you see what are the consequences for small scale power. So it's really important also because I remind you that in the large scale structure there are some nonlinear effects at small scale, like for example peculiar velocity in virialized halos, right? This finger of God effects is intrinsically nonlinear effect. So you might want to do things properly at small scales. Okay. Again, you see this is a difference in the signal, simulated signal, on whether you put the H1 at the center of the halos or you model it accordingly to its actual profile. And you see there is a difference of nearly an order of magnitude at small scales. And the small scale will be accessible by the experience. So you want to do things kind of accurately, okay? So the other thing that I want to address is word dark matter. And word dark matter works like this. We'll be talking about this maybe in the next few lectures, but basically suppresses small scale power. Right? And so at some point, basically you're saying, okay, I have two universes. One is lambda cold dark matter, the other one is warm. And the warm, I don't have the small scale halos. Okay, now I have a total amount of H1 that I need to put into these halos, and this amount of H1 is fixed in the two universes because it's observed with absorption lines. So that is a number, okay, very, very nicely measured. So then what I do, I start to populate these halos with H1, right? The warm dark matter, the cold dark matter. But at some point, in the warm dark matter, I don't have any halos anymore. And so what I do in order to fulfill the same constraint of the lambda cold dark matter is I tend to put slightly more H1 into more massive halos in the warm dark matter as compared to the corresponding similar massive halos in the lambda cold dark matter, okay? So it's basically as simple as this. And so these massive halos are typically more biased, and thereby a suppression of small scale power produced by the free streaming of dark matter, thermal dark matter, sterile neutrinos, manifests itself as a boost of power in the H1. And this is what you see here, right? We were surprised to some extent to see this 50% boost of power at this scale of K of 1 at redshift 3, 4, and 5. These are two different ways of populating the halos. And these are the noise of the instrument. So you see the small scales are not accessible because of thermal noise of your instrumentation. And so we said, okay, but if small scales are not usable, then we cannot see the free stream, right? But no, luckily for us, this signal is boosted also at the larger scales for warm dark matter scenarios. Okay, this is a possibility, of course. Another possibility is to use higher order statistic, like the bispectrum or the 3-point correlation function. This will be more sensitive to the topology, so it's a higher order information, if you wish. And well, I don't maybe dig into the details. You can ask me if you're interested in the bispectrum, but basically you see here these two scenarios have the same power spectra for 2, 3 and colder and 2 kV and 3 kV and colder matter up to K of 1. But in terms of bispectra, they are radically different up to a factor of 300%, right? For a particular configuration of the triangle. So you pick up really the warm dark matter free streaming in this way. I believe this is maybe a more promising avenue. Maybe let me skip this because, well, we might just mention that, you know, here, what you see here is the MCMC, Bayesian statistic, the measurements of these parameters, right? H0, sigma 8, NS, the parameters of the lambda cold dark matter. Here we are purely in cold dark matter. And we ask ourselves, what is this experiment able to do on its own, right? Regardless of any other data combination? And the numbers, maybe, you know, you see it here, it's not particularly precise, of course. But then when you add the CMB, the improvement compared to Planck only could be up to a factor 2 for H0, H0 and sigma 8. So the point that I want to make here is that really I like to combine only two observables at a time because I understand better what's going on, right, rather than combining more. And of course, if you take Planck with BAO, with supernovae, it's very, very constraining at the level of this or more than this, actually. But if you put just Planck and this, you will be at the level of BAO, right? You have a power spectrum measurement, shape, which can help to measure, you know, to address these things that you might have heard about the tensions. So in terms of modified gravity, there are also some functions in an EFT description of the dark energy that could be constrained by this. One of these functions is this omega EFT that in some way describes also a coupling between dark energy and dark matter. And we ask ourselves whether this observable can constrain omega 0 FT and beta. Beta is the redshift evolution, the running, let's say, of this parameter. And the point is, well, there are many numbers here. The point is that anyway, that you can improve over Planck in terms of beta at the level of 10%, in terms of omega EFT at the level of 24, 26%. I remind you, these are Planck real data and forecast for 21 centimeters of experiments hopefully happening in the next 5 years. So again, why do we need this data? Well, because these observables really probes the redshift, those redshifts at which this number here is expected to run, right? Is expected to show a departure from lambda CDM. That's why. Neutrino free streaming. What you see here again a simulation of the data, monopole of the power spectrum, quadrupole of the power spectrum. The shaded area here is really the neutrino free streaming. It's really what you would expect if you let just the neutrino mass free in a reasonable range between the minimal value, right, and 0.6, which is a very conservative 2 sigma upper limit. We have maybe 4 sigma upper limit now. And so you see the shaded area here is very much, in a regime in which your data could be measured with exquisite, precision to some extent. And also, what you see here is that maybe the degeneracy, you see the Planck is like this, sigma, total neutrino mass sigma 8, and then you have intensity mapping going in this direction. So you kind of tend to break, they have different degeneracies. Okay, so far so good, very nice story, very good numbers, but in reality we do have, skeleton, things, very, very bad things to deal with. One is the foregrounds. And the foregrounds for 21 centimeters is a very serious aspect, right? It's a very serious problem, unlike CO and C2 line, because in that case, the sub-millimeter experiments, you typically use SPT telescope, you plug in some, they call it spectrometer, and there are experiments in this direction. And so you use the kind of technology already present for CMB, stage 4 or whatever experiments. But here the foregrounds are really a nightmare. And the foregrounds come in different flavors. They come in terms of galactic foregrounds and extragalactic foregrounds, and you have to clean them up, and it's difficult, right? And so they are typically many orders of magnitude larger than the H1 signal, which is here. And you see you have to clean them up. The signal is wiggly, it contains structure. They typically are very correlated in frequency, so they are smooth. So that's the big thing that helps. To some extent, because polarization, this radiation is also polarized, and polarization leak into intensity with structures. So there is also this polarization leakage that complicates things further, right? And so there is a huge literature about it that you can read. Yes. And so at the end, your post-organization window is a bit more appealing, right? You have cosmic variance. This is the K parallel, this is the K perpendicular. The cosmic variance, of course, will set a limit, especially to K parallel. Then there is the field of view, which sets a limit on K perpendicular. Then there is the array configuration, okay, which sets a limit to the smallest scale that you can probe in the transverse direction. Then there is the spectral resolution up here. And then here there is the foreground, the so-called foreground wedge that you tend to remove also because of polarization leakage. So if you want to be extra conservative, you say, okay, I just sit here and I want to investigate things here. But there are people who are brave enough to kind of, try to address also this thing here, try to reconstruct the power there, because there are lots of modes there. There is lots of statistics, right, if you can clean it up. And one way of cleaning things up is to cross-correlate with galaxies, right? Because we know galaxies much better to some extent. And by cross-correlating, you basically get rid of the noise, right? So if you think about this, the autocorrelation of optical, which comes in with the noise, and this is the source and the noise, right? These are correlated. This is, again, you can write it like this. And this is the radiometer, the cross-correlation between intensity and the optical galaxies. And you single out the thing that you really want under the assumption, which is maybe reasonable enough, that the noise in the optical and noise in the intensity mapping are uncorrelated, two different experiments and things like that, right? So it's really, and I remind you that this you can study very well. We will see lecture number 3. So people did that. This is Laura Waltz. You see this the H1, this is the H1 in autocorrelation and cross-correlation. And you see you have many different colors. What are these colors? These colors are when you take out the foregrounds by using principal component, right? Principal component, you might know what it is. It's a technique to remove, the foregrounds. And what you learn from this is really that it is sensitive to the number of principal components that you take out, unless you are at the smaller scales like this, which is kind of more stable. So out of this complex plot, they basically carried out a measurements like this, in which at least for some configuration, they do find an evidence of signal. Okay, this is maybe a 3 sigma, but this year, a few months ago, with the Meerkat, which is a precursor of the SKA, they did a similar thing, but with other set of galaxies, the Wiggle Z galaxies, I believe. So you see, it's a small patch of the sky in which you have galaxies, and this is the intensity. You see, this is Kelvin. This is the millikelvin after you clean them up with the foregrounds, having 30 PCA components, and this is the cross correlation. And the thing that convinced them that they did the right thing is that once they randomize the position of the galaxies in the cross correlation, the signal vanishes. This down here. And this is a 7.7 sigma detection, which is really, I believe, interesting, because it sets the way, it really paves the way to, realistic quantitative cosmologies with this. Systematics, let me skip this. People working on GR or relativistic effects, they might know that the general way to work out a perturbation to galaxy number counts involves an equation like this, in which you have the density term, you have the Redshift space distortion, but you have also, let's say, higher order correction to this, which are basically produced by the potentials, right? Produced by the potential, but the lensing. And people are after this. You see, this is what this power spectrum will look like if you use different gauges. So you will have an enhancement of power at the larger scales. And these intensity mapping experiments are ideally tailored for such a test, because they will probe large volumes. Relativistic best spectrum, let me skip. I also skip this. Another thing, since we are before talking about inflation, and I'm nearly done, just 1 more minute. Inflation predicts some non-Gaussian, primordial non-Gaussianity, right? And this non-Gaussianity can be tested with large-scale structure. It's tested at the CMB level, but the large-scale structure are kind of promising in this respect. And so, how do you look for this non-Gaussianity? You look at basically an effect that it has on the large-scale structure. It changes the bias of the halos by enhancing them with this non-Gaussian correction, which is related to the shape of the bispectrum, which is this function here, okay, which is a correlation, which is a convolution with the bispectrum with the window function. Let's say it's a kind of complex, but not so, I would say. And basically, you have this enhancement, which is related to this FN local, NL local, which is this parameter that inflationary people are very much interested in. And so basically, this enters here and enters here. And then you plug this into your machinery, and you see the correction to the bias that you will have at the larger scale. And for this particular local non-Gaussianity, this is for FNL equal 1, you have an increase in the bias, which is significant compared to, let's say, the 0 case. So you have really a correction to the bias at the Redshift 4, which is really significant. And people made forecasts for this. So it's really another possible way to look at inflation. So let me conclude. I showed you a kind of quick overview on the importance of intensity mapping to perform quantitative cosmology. So really, the universe is our laboratory. We'll measure something. Intensity mapping is still pristine compared to other probes, right? Because there are fewer experiments, mainly in cross-correlation. But nevertheless, can be used to address some scientific questions like baryonic acoustic oscillations, neutrinos, dark matter, cosmological parameters. And so the efforts are at the moment focusing on foreground removal, to be more precise, let's say in determination of the large-scale structure behavior, and to see maybe, the foreground removal. We saw that principal component removal is very much, polluting to some extent the large-scale power, and so it can, spoil our attempt to measure, for example, FNL. Thank you.
Hi. Okay. So at which redshift do you expect the 21 centimeter signal to begin to be visible? Because there is neutral hydrogen, right? But what controls that this spin flip transition actually happens?
So, okay, that's a very good question. So during reionization, Okay, there is lots of astrophysics, right? So the astrophysics of organization causes a complicated, let's say, interplay between the actual signal and the actual signal that you see and the astrophysics. Okay, so for example, you have to follow, if you want to follow organization, you have to follow, for example, I don't know, if there are X-rays, for example, heating up the intergalactic medium, you have to follow the the Lyman alpha UV luminosity. You have to follow, for example, radiative transfer effects. But after that, and here we are after that, things get simpler. You're less prone to astrophysics. So in a way, it's always visible, right? It's visible in the galaxies near us, but here it's not what we are after. We want really to have an integrated view to this. And so basically the 21 centimeter is always emitting. And typically spiral galaxies are full of it, right? And so you typically see this in spiral galaxies if you might want to think about a tracer. But you don't have to think about just in a way focusing on this. To some extent, there are also groups of galaxies that they retain H1 also in the surroundings. So it is in the galaxies, but it's also as a kind of more diffuse than in galaxies. Unlike the CO, which is much more focused in the star-forming regions. So my answer to your question is that if you are after ionization, as we are here, you do expect to see it everywhere. Yeah.
Hi, Matteo. Thanks a lot for the nice talk. I wanted to ask, in your opinion, until which redshift we can confidently model H1 distribution by populating halos, and like in this one halo and two halo term split, and then until which redshift onwards we need like to take into account that there is also H1 outside halos.
Yes. Okay. So let's say I know this number because with simulations, we know this number. And let's say by redshift 4 or 5, at redshift 4 or 5, the amount of H1 which is outside the halos is at maximum 10% according to simulations. Okay. So in a way, we will not be accurate. If you use a halo model approach, you are not going to be accurate if you neglect this component at the level of 10%. But there is another thing that worries me a bit more, because this you can always, kind of model this to some extent by having a more refined halo model. What is worrisome for me is that in these halo model approaches, sometimes you also populate halos according just to their mass. Okay, and this, for example, does not take into account about the assembly bias. Okay, tomorrow will show, or the day after tomorrow, two distribution of galaxies which have the same mass, and they have a very different clustering pattern because they are formed at different redshifts. So in a way, what worries me most is not the mass which is outside the halos, the H1 mass, but I would like to have a much more refined halo model, which takes into account, for example, assembly bias, which maybe takes into account the disk of the galaxy. There are some models. Ojumo, for example, has more semi-analytical models, and so I believe that there is more work to do in this direction rather than worry about gas H1 outside the halo. But it's a good question, of course.
Okay, great, thanks. This is also connects to another point I will ask you then in the coffee break.
Okay.
Hi. When talking about neutrinos, are you assuming that you have 3 degenerate neutrinos, or
yes?
Do we expect to be sensitive to the mass difference at some point, or?
No, I mean in this cosmology is to an incredibly good approximation sensitive only to the total neutrino mass. Okay, so in reality there is a sub per mil effect on the splitting, but you're sensitive to the total neutrino mass. So all the things that I showed you are either based on this assumption in the modeling, but also in the N-body simulation with neutrinos, we have a neutrino fluid which is degenerate and which is carrying the whole neutrino mass, which will vary typically between 0.06 and 0.6 eV.
Okay.
Yeah.
Thanks.
Thank you for your talk. At some slide, you showed that you can rule out warm dark matter at 4 keV mass with some like 5,000 hours of exposition. I wanted to ask, what is the status then of 3.5 keV line, is it excluded already because it's 7 keV particle, or when can it be excluded or confirmed?
Okay, so these numbers that I showed you, 2, 3, 4 keV, they refer to a thermal or dark matter particle. They do not refer to the sterile neutrino, which is typically advocated to explain this line that you were talking about, that with 7.1 kV, which could give rise to a line of 3.55 kV that people have seen in some X-ray observations. I believe that the status of this line is a bit, in a way, quieter now, in the sense that there is something in the spectrum, but is not, there is no consensus on whether to interpret this little bump that you see in the spectrum as a sterile neutrino line. So my opinion is that there are people like Boyarsky working on these things. They advocate this explanation. I'm not an X-ray expert, so my point is that I think I heard that there are fewer and fewer people talking about this line at this very moment. This doesn't prevent, of course, the possibility that there is a sterile neutrino. So to answer, I haven't really answered your question. I believe that these 2-3 kV, they refer to different scenarios in a way. Okay, so but nevertheless, you can test this with intensity mapping. Bye.
Hi. So in one of the slides, you showed the simulating intensity mapping signal at small scales, and where you compare the, I think, the power spectra for simulations and the putting H1 by hand in the center of halos.
Yes.
So I didn't get the point. Which one is correct among these?
Well, the one which is correct is the continuous line, not the shaded one, right? The shaded one, you put it at the center. In the other one is full hydrodynamical simulation with all the possible physics, provided the physics is correct, of course. And you see, basically, by putting it in the center, you really have in a short noise term which cancel the power up to the larger scales, right? So it's somewhat larger scale. In the other case, you do have structure, and this structure, so it's in a way is more diffused, and so it's smaller, right?
Okay.
So the most physical case is the continuous line in this case.
Thank you.
But you can read this paper by Villascusa Navarro, because if you suppose, there are people like this, suppose you measure only the shot noise, you can say, okay, why shot noise is not good? No, the shot noise term in this interpretation retains cosmological information, because you see in the shot noise term evaluation, there is the mass function which could carry cosmological information.
So my question was more in the foreground thing. So I guess the thing that, of course, if you cross-correlate with galaxies, then you get a clear signal because you know what you are looking for, basically. But I guess that the power of H1 is mainly to go to high redshift where there are no galaxies. So what do you think that it's going to be possible to clean the foreground so much that we can like get the signal in autocorrelation and not in cross-correlation? So you can do the foreground cleaning both for the autocorrelation, both in cross-correlation, right? Cross-correlation is a bit better in the sense that it seems that now it's going to provide actual measurements, right? Unlike the autocorrelation, which is really upper limits or something, you are measuring actually the noise. So at some point you will be running out of galaxies, but there is going to be other traces, right? For example, there are, for example, people who are thinking of cross-correlating with the CMB lensing, right? That's also another possibility. You can cross-correlate with the Lyman alpha forest. So there are few other tracers, but I believe at some point, right, this foreground thing will be solved, right? In the sense that, for example, there are also machine learning techniques. People are working on this, right? So there are several different aspects of generative models, PCA component analysis that are more refined. So at some point, I believe this foreground problem will be either solved or very much cornered in a corner and kind of placed under control to some extent.
Oh, thank you, Matteo, for this very nice review on density mapping. I'm sure there are many more questions. Well, I personally have many more questions, but I will address them during the coffee break, because otherwise we're going to run over the time of the coffee break. Just to tell you that today the coffee break is going to be in the opposite room, in the microcosmos room. Sorry, we could not set up all the coffee thing in the terrace because it was windy. Yet it's a beautiful day today. You can see Gran Canaria. So, but please refrain from taking coffee or any type of food or drinks outside this room, because that's forbidden. You can have your own coffee, and if you have time, then you can go up to the terrace. See you then in half an hour, right? Thank you.